Hi, and welcome again to this series of videos on structural dynamics. When vibrations are excessive in a structure, a possibility is to dissipate this energy to lower the levels of vibration. And this is done by using damping. So adding damping, as we have seen in the video on 1 degree of freedom system, will be effective mainly around the resonance of the system. So basically the amplitude at resonance is limited by damping, and if you multiply the damping by a factor of 10, you will have an amplitude that is divided by 10. What are the sources of damping? So damping is a dissipation energy, and damping can come from internal effects, such as the damping in the materials, the connection, the joint, the bearings, but also from external effects like non-structural elements attached to the structure, and in the case of buildings, energy radiation in the soil. Now, all these kinds of damping models call for local damping models, as the damping is not uniform throughout the structure. So damping can have different origins, and let's have a look at damping coming from materials. One way is to increase the damping is to put materials which have more damping. The damping models are typically viscous damping, where the C matrix is proportional to the stiffness matrix, and the value of alpha can be different in each material. You can also use models with loss factor, which is called hysteretic damping, in which case you are using a Young's modulus in the material, which has a real part and an imaginary part. And the imaginary part is responsible for damping, where eta is called the loss factor and can be a function of the frequency. When you go to a structure with several modes, then damping can be translated to modal damping coefficient. So each mode will have its own damping coefficient, which, if the structure is uniform and the loss factor is the same everywhere, will be equal to psi a equal eta over 2. Typical values of these damping coefficients for different materials, like reinforced concrete here, is about from 0.4 to 1.2%. Composite is lower, and steel is also very low, from 0.1 to 0.2%. Now, when you have different materials, this psi I is a function of the different damping mechanism, whether it is viscous or hysteretic. Now, coming back to the origins of damping, we just discussed material damping, but for connections and non-structural elements, it is much more difficult to have quantitative values of the damping brought by this element. Typically, as discussed before, a value for psi in civil or mechanical engineering structure is about 1%. And so you see that this is quite higher than the values for the materials themselves, where steel, for example, is 0.1%, so that a lot of dissipation actually comes from these connections or non-structural elements. Which means that in practice, because these values cannot be assessed beforehand, damping coefficients are usually derived from practice, so if you already know about a type of structure, or measured. There are two simple methods to estimate the damping of structure. One is called the logarithmic decrement method, and it estimates psi in the time domain, and the second one is called the half-power bandwidth for an estimation of psi in the frequency domain. The idea of the logarithmic decrement method is to take two amplitudes of peaks which are separated by m periods. So we know that the free response for a 1 degree of freedom system is given by this expression, and so we are looking at this expression at value x of t and x of t plus m periods. So what you see that because it's periodic, this cosine and sine function is equal to this value, so that when you do the ratio of the two amplitudes at time t and t plus mt, you are left with e to the power of psi omega n mt. Now we are going to take the logarithm of that, and the logarithm of that will give us psi omega n mt. And then we will replace the mt, so the t, by 2 pi over omega d, because this signal is oscillating at frequency omega d. We end up with this expression, which shows that if psi is rather small, which is the case for typical structure with 1% damping, then the damping is given by 1 over 2 pi m lambda. So this is a very efficient way to measure the damping, usually on the first mode of a structure. Why on the first mode of a structure? Because we have seen in the chapter, in the video about multiple degree of freedom system, that if you look at the impulse response of an MDOS system, you will have a combination of impulse responses of all modes, but the modes at higher frequency will decay faster. So if you wait a little bit, maybe in the beginning you will have the higher frequency, but at a certain point you will have only the response of first mode, which allows you to identify the damping of this first mode. The second method aims at estimating psi when you have a response in the frequency domain. So consider this frequency response function, and you identify the maximum here as A. Then you look at the values of frequencies which correspond to A divided by square root of 2. Actually, this method is called half power bandwidth because the power, which is the square of that, so if you look, for example, at the power spectral density of the signal, you would then look at half of the maximum power. So at half power, or A divided by square root of 2 for a displacement, you will have two frequencies, capital omega 1 and capital omega 2. And this bandwidth here between is used to assess psi. So if psi is smaller than 10%, then you can estimate psi by the difference of the bandwidth divided by omega 2 plus omega 1. It's also possible to increase the level of damping due to materials by using some damping treatments. There are two main types of damping treatment. The first one is referred to as unconstrained layer damping. The idea is that you have a base layer here of a material which has quite low damping, and then you add or glue to it a damping layer. So this is made to function either in traction or in bending, which also induces traction here. And so the damping layer here works in extension. Another way to add damping is to use constrained layer damping. In this case, you are putting a damping layer and then on top of it a constraining layer made of a material which is usually similar to the base layer. In this case, the material here in damping is used in extension but also undergoes some shear, which tends to increase the damping because some materials have more damping in shear. Those materials, those treatments have a quite broadband effect and affect all the modes of the structure. An example of unconstrained damping layer is shown here, where the floor pan of an automobile is treated with some asphalt, with a sheet of asphalt which is melted on the top to increase the damping. This video here will demonstrate the effect of these constrained damping layers. So visually these two elements, two cantilever beams, are the same, but one is just made of aluminum and one is made of constrained layer damping. So this one has very low damping while this one has very high damping. Another example of constrained layer damping is given here. So one of the balls is made of metal, and on the other one, in the inside, there is some constrained layer damping added, glued inside the ball. And now you're going to hear the difference when you knock on the ball. This ball, because it's not damped, will ring, while the other one with the damping will not ring and will make a very small sound. Another example in the construction industry is given by a damping treatment here added to this bridge as shown in the video.
Stockholm is growing, and with new developments comes greater urban concentration, as we see here at Årsta Bay. The new buildings lie in close proximity to two railway bridges across Årsta Bay, and passing over these bridges is the entire rail traffic in and out of Stockholm in a north-south direction. One of the bridges is a modern red concrete construction. The other bridge was built in 1929 and has been classed as an historical landmark of exceptional quality, with an arch bridge of steel in a classic truss superstructure. The old Årsta Bridge has a twin track, and a train passes along the bridge every 6 minutes around the clock. The old Årsta Bridge has recently been renovated and reinforced. When the bridge was reopened for train traffic, it was noted that the noise levels had increased in comparison to earlier levels. The noise had to be decreased, and the task to accomplish this was assigned to Vibratech. A big challenge was to find a solution that could be implemented without disturbing the constant rail traffic. It could be proven that the noise came from vibrations in the steel structure, and that the increase was mainly in low frequencies. A solution could have been to introduce a vibration isolation under the track. This would have decreased the vibration entering into the bridge's structure. But because the transport agency required a solution that did not disrupt the rail traffic, it was impossible to accomplish. All measures to be taken must occur below the bridge deck to enable normal service to proceed. Vibratech chose to test a noise damping technique known as constrained layer damping, CLD. It entails that a noise damping material is pressed, constrained against the steel structure of the bridge. The vibration is catched between the steel plates and dampened in the constrained layer. In order for this to work properly, there must be full contact between the surfaces of damping material and steel. Another problem to consider is that the damping must function during winter as well as summer. Vibratech built a full-scale mock-up model of a bridge beam and undertook a number of tests of various damping materials, different thicknesses at both plus and minus temperatures. The results from these tests could then be put into a computer model of the bridge. By use of statistical energy analysis, SEA, the future noise reductions could be calculated for different materials. Vibratech could conclude that damping the bridge structure would result in a 6 decibel noise reduction using the CLD method. On the basis of this analysis, the transport agency decided to implement measures for the noise damping of Årsta Bridge using constrained layer damping panels. Work began in the autumn of 2017. First of all, 66,000 bolts had to be welded in place. The bolts were closely positioned to achieve the required pressure on the panels and the firm contact between the damping material and steel structure. The bridge deck and its beams were all covered with CLD panels. Meanwhile, the trains continued to pass just 2 meters above. Before any mounting could begin, the surfaces were carefully cleaned to ensure an optimal contact between the noise damping coating on the panels and the steel structure of the bridge. Following this, around 5,000 panels were fitted. There were 270 different shapes to make sure that every part of the bridge could be covered. The panels were painted in the same color as the bridge, not to affect its appearance, which was important considering that the bridge is classified as an historical landmark. To ensure effective damping all the year round, the panels contain 2 types of damping material, one being adapted to warm weather and the other to a cold climate. The installation continued into the summer of 2018. After this, the noise levels were measured to validate whether the operation had had the intended effect. Vibratech had used the CLD technique on earlier assignments, but this is the first time it has been applied to a steel bridge. An overall decrease in noise is welcome, but most important is that the disturbing low frequencies have been filtered out, so that residents in the area are less bothered by the flow of rail traffic.
So these kinds of constrained layer damping, so multiple layer damping systems are applied, for example, also in aeronautics, so in panels of aircraft, or in wood construction as shown here. Damping involves some quite complex physical phenomenon, and this is very difficult to model. So the idea here would be to find some kind of equivalent model which can be based on some basic measurements of the dissipation that exists in a structure. So when dissipation is present in the structures, the stress is not in phase with the strain. So when this is the case, if you represent stress as a function of strain, you have a so-called hysteresis loop. The mechanical energy that is dissipated in one cycle per unit volume is given by the area here inside the loop, because this integral, sigma epsilon dot, can be written as sigma d epsilon over dt dt, and dt disappears, and we have the integral of sigma d epsilon, which is the area here. E pod here represents the maximum potential energy, so when the stress is maximum in the structure. So the damping factor of a material is defined as 1 over 2 pi times the energy dissipated in one cycle divided by the maximum strain potential energy, as is noted psi. The damping factor for a structure is the integral of this value over the volume divided by the total volume, so it's an average energy dissipation per strain energy, and is given by 1 over 2 pi times the energy dissipated in the structure in one cycle divided with maximum strain potential energy. In the case that the structure is homogeneous, then we have psi is equal to psi s. To compute the damping factor for a single degree of freedom model with damping, we start from the equation of motion, and we write the energy dissipated here in the dashpot as the integral of bx dot x dot dt, so this is the force times the velocity. As we know that x of t follows a cosine for a given excitation frequency, we know that the dissipated energy can be written as the integral of omega squared, so because we translate x to a velocity, so it becomes j omega x cos omega t, so we have a square, so we have omega square b times the amplitude square times sine square. And by integrating, we get the result that it is equal to omega square b times the amplitude square times the period over 2. So as we know that the period is 2 pi over omega, we end up with pi b omega x square. We now need to compute the maximum strain energy, which here is given by 1/2 times the stiffness of the spring times x max square. So if x is given by this formula, then the maximum is the modulus of x, and this is the potential energy. We can then write psi s as 1 over 2 pi times the ratio of these two quantities, and we get the simple expression psi s is omega b over k. Now if we look at the resonance, so when the frequency omega corresponds to square root of k over m, then it simplifies to b over square root of km, which is actually 2 psi. So the value of the damping factor for an SDOF system is twice the damping coefficient of this SDOF system. Now we are going to discuss the idea of equivalent viscous damping. So in a structure, of course, the damping is not viscous and the structure is not a single degree of freedom system. So the energy dissipation as a function of frequency might have any kind of form. So since we know that psi s is omega b over k, we could say, okay, we can find a b, but then which is frequency dependent, which is k psi over omega. The problem is that then we introduce a b that depends on the frequency, and so for time domain computation it's going to be difficult, while for frequency domain computations we could use that approach. So another approach that also works for time domain is based on the fact that we know, and we already discussed the fact that for a single degree of freedom system the effect of damping is only around the natural frequency. So it is only important that the actual damping matches the equivalent one around the natural frequency. So we are going to use this viscous damping, which brings a line in this diagram equal to the actual damping at the natural frequency. So what we want is to have a psi s equivalent is equal to omega b equivalent, which gives the slope of this line, over k at omega is equal to omega n. And if we equate the two at that frequency, we show that b equivalent must be equal to psi s at the frequency omega n times square root of k times m. So let's take two examples. The first one is hysteretic damping, where the psi s is constant, equal to 2 psi, and therefore equal to eta, the loss factor of the material. In this case, applying the equation gives us b equivalent is equal to eta times square root of km. The second example is Coulomb friction damping, a slightly more complicated example, where the force, the damping force, is given here by this expression, where this is the Coulomb force multiplied by the sine of the velocity. So if we look at the signals, we have the displacement here, harmonic displacement of the mass, we have the velocity here, and every time the velocity changes sign, the force, the Coulomb force, will change sign as well, where the amplitude, however, will always remain the same. Now, if we plot that in an fx diagram, we see how fc will change with x, and the dissipated energy is given by the area or under here inside this rectangle. So it is equal to 4 times fc times x. The psi s being the ratio of the dissipated energy over one cycle divided the maximum potential energy, which is 1/2 kx squared, we end up with psi s is equal to 4 fc by kx. This means that the equivalent damping is given by 4 fc over pi omega nx, and we have a damping which depends on the amplitude of motion x here, so it is a nonlinear damping coefficient. This video gave you an overview of how to add damping into a structure using a material or special treatments, and detailed how to make an equivalent model. Damping is probably one of the most widely used solutions against vibration and resonance in engineering, and this is why it is very important to understand how to add damping and how to model the effects of damping on structures.